in the first unit of nuclear and particle physics, we will start the study of nuclear force by discussing the force between nucleons. And the Deuteron is taken as an example for this. So we can start with the characteristics of nuclear force. Even before describing any further experiments to study the force between two nucleons, we can already guess at a few of the properties of the nucleon force. And they are: at short distances, it is stronger than the Coulomb force. The nuclear force can overcome the Coulomb repulsion of protons in the nucleus. At long distances, that means of the order of atomic sizes, the nuclear force is negligibly feeble. So, the interactions among nuclei in a molecule can be understood based only on the Coulomb force. And some particles are immune from the nuclear force. There is no evidence from atomic structure, for example, that electrons feel the nuclear force at all. And as we begin to do experiments specifically to explore the properties of nuclear force, we find several other remarkable properties. The nucleon force seems to be nearly independent of whether the nucleons are neutrons or protons, and this property is called charge independence. The nucleon force depends on whether the spins of the nucleons are parallel or antiparallel. The nucleon force includes a repulsive term which keeps the nucleons at a certain average separation, which means that they cannot be very closer, normally of the order of less than 1 Fermi. The nucleon force has a non-central or tensor component. This part of the force does not conserve orbital angular momentum, and normally orbital angular momentum is a constant of the motion under central forces. So now we can discuss the Deuteron, because the Deuteron consists of a neutron and proton. That means a neutral atom you are calling as the deuterium, and its nucleus of the deuterium atom is termed as Deuteron. So it is the simplest bound state of nucleons, and therefore gives us an ideal system for studying the nucleon interaction. For nuclear physicists, the deuteron should be what the hydrogen atom is for atomic physics. In atomic physics, we start with the study of hydrogen atom. That means it is the simplest atom with simplest atom with only one proton and one electron. And here, when we are coming to the nucleus, for studying the nuclear force, the basic requirement is two nucleons, and that structure is with a proton and a neutron, and that is your deuteron. Just as the measured Balmer series of electromagnetic transitions between the excited states of hydrogen led to an understanding of the structure of hydrogen, so should the electromagnetic transition between the excited states of deuteron lead to an understanding of its structure. But unfortunately, there are no excited states of the deuteron. We have already studied the energy transition between in Balmer series from a particular energy state to the lower state. It emits an electromagnetic radiation. Suppose you measure that electromagnetic radiation, you can get the difference in energy levels, etc. These uh, type studies can be made. But for a deuteron, there is no excited state. It is such a weakly bound system that the only excited states the only excited states are unbound systems consisting of a free proton and a neutron. So, since they are weakly bound, you can say that their binding energy is somewhat low. So, now we can study or we can discuss some properties of deuteron. The deuteron possesses measurable properties which might serve as a guide in the search of the correct nuclear interaction. And these properties, we will start with the binding energy. The binding energy of the deuteron is a very precisely measured quantity. The observed value is 2.224, or sometimes you can take it as 2.225. The average binding energy per nucleon is about 8 MeV. You can see that the average binding energy per nucleon means for our stable nuclei, you are normally finding it as nearly 8 MeV. And here, the average binding energy per nucleon means again you have to divide this with 2 because 2 nucleons are there. So it is very low. So the neutron is therefore very weakly bound compared with the typical nuclei. And how can you measure this binding energy? A large number of direct and indirect methods are there, and we just go through them. First one is a mass doublet method. Here you will use two nearly equal masses, and you can use in mass doublet method means using mass spectrographs. You might have studied the Aston mass spectrograph, etc., in your chemistry classes. So, the way in which a mass spectrograph is working is not at all important at this point. We just mention that term and we will discuss the values that we are getting from the apparatus. So, this is the case. You are using two nearly same masses having the same value of mass number, and this is important, same value of mass number. In the mass spectrograph, both ions, normally you will be using ions of that, ions are produced simultaneously in the ion sources and are focused as two nearly lines. After this discussion, we can just see the structure of a mass spectrograph. So, this is a mass spectrograph, and here you will be producing some type of ion sources, and it is passing through an area. You have seen this velocity selector, and you have studied that when a charged particle is entering into a magnetic field, it is experiencing a force mv square by r. That means it is in a circular path equal to qvb that you are writing. That means it's charge into velocity into magnetic field. So the force you can take as qvb, and the force due to electric field is q into e. Suppose this QE and QVB are same. That means you can simply get as QVB is equal to Q into E, or simply you can Q and Q cancels. V will be equal to E by B if its velocity is such that it is equal to ratio of E by B. That means it is not experiencing any force. The electric force and the magnetic force are normally in opposite directions. They will cancel each other. So that velocity is means that is the velocity selector. That means you are considering that. So other charged particles, they will experience either electric field or magnetic field. If electric field, they will move towards one direction, either positive or negative charge. Similarly, in magnetic field, they will move in circular orbit. So, if an ion beam is entering like this, it can't move along a straight path and it will have some deflection either towards upper side or towards downside. So, it will not come through this slit. So, only that means you will be adjusting that particular mass to be passing through this. And under the action of magnetic field, you can see that here there is no electric field, only magnetic field. In the magnetic field, the magnetic force QVB equal to mv square by r. So there, that mv square by r, if there is a small deviation in mass, that means that QVB is a constant. It is equal to charge, and that charge is independent of the mass. So that mv square by r, that m and r are dependable terms. So when m increases, r also has to increase then to keep that m by r constant. So you can see that the particles with the more masses will make an orbit which has more radius. That is, you can see here. So this will be the lowest mass and this will be the largest mass. So if that masses are very near, these two paths will be very near. That means you will get two nearby paths, and you can record this either on a photographic plate or on a screen, etc. And from that measurement, you can have an idea about the mass, and that is actually we are doing in a mass spectrograph. So the formation of hydrocarbon with a great variety of mass numbers provides a convenient method of mass comparison with the doublet method. Here you have an S is missing of mass comparison with the doublet method. And we have mentioned that the mass number must be almost same. So here you are using this that difference in masses you can directly measure from that. So you are using two compounds, hydrocarbons, C6H12, its mass minus mass of C6D6. This D stands for H2, that means your deuterium, and its nucleus is your Deuteron. So you can see the C6H12 minus mass of C6D6 is 9.289710 plus or minus 0.000024 10 raised to minus 3 U. As you know, this U is the unit for atomic masses or nuclear masses. And similarly, you are also using the term AMU, atomic mass unit. And the difference between AMU and U is that AMU means it is the unit defined based on the mass of oxygen. Initially, it was defined as mass of oxygen is equal to 16. So 1/16th of mass, that you are calling as one atomic mass unit. And later we have changed from oxygen to carbon. And in the case of carbon, the mass unit you are simply writing as U. It is 1/12th of mass of carbon. And it is that you can take as 1. So 1 U. So thus the difference in mass will be very small. This is of the order of milli-u or small mu. And we have mentioned that the total mass number, here you can see that carbon mass number is 12. You have 6 atoms here. So 6 into 12 is 72. And you have 12 hydrogen here. So 72, that of hydrogen is 1. So 1 into 12 is 12. So 12 plus 72 you are getting as 84. And here 12 into 6 is 72. That of D or H2 is 2. So 2 into 6 is 12. Again 12 plus 72 is 84. So this almost same mass number you have to use. You are getting this one. And one more is here. It is C5D12. It is 12 into 5, 60. 2 into 12 is 24. So total 84. And mass of C6D6. C6 means 12 into 6 is 72. And 2 into 6 is 12. Again 84. So equal. And that is 84.61 something into 10 raised to minus 3u. And from this, how can you measure the mass D6? From the first one, you can write as this equation. M of C6H12 minus M of C6D6 is equal to this value. So this you are writing as mass of carbon. That means 6 times. 6 times mass of carbon plus 12 times mass of hydrogen. And here 6 times mass of carbon minus 6 times mass of deuterium or deuterium. That is equal to, and here we are considering only the ion. Or if your electron is there, you can neglect the mass of electron. This is this value 9 point something. Here this 6C and 6C cancel. So it is 12 mass of hydrogen minus 6 mass of deuteron is this value. And now you can use this number. This is known to us 1.007825037 U for the hydrogen mass, H1 mass. We are actually here not using this mass number 1. So 12 into that number minus 6 is this one. Or from this mass of D or mass of 2H, taking this to this side, and here it will be nearly 2 or 6 by 2, or you are 12 by 6 you are nearly getting as 2.014 something. And this uncertainty plus or minus, for getting this you have to use the techniques in error analysis, and we are not going into the details of finding this one. And here it is 0024 and here it is less than that value, and we are not going into the details of this calculation, but this you can directly do. You multiply this and subtract this number from here, this 12 into this number, and divide by 6. That number will be this one, no doubt. And for the second one, similarly you can write as 5 times mass of carbon plus 12 times mass of D, 12 times mass of D minus 6 times mass of carbon minus 6 times mass of D or deuteron. And now you can use 12U for C12 mass. Here you have minus C, and this 12 minus 6 you will be getting as 6. So this 12 can be go to this side. So 12 plus this value, and when you are dividing that with the 6 here, you will be getting this number. And these precise values are in very good agreement. You can see both values are nearly same. And we got the mass of deuteron now. But our aim is to find out the binding energy, that we can find by this method. With this mass of 2H and using the measured 1H and neutron masses. 1H means your proton and this is neutron masses, we can find the binding energy. Or similarly, that 1h means you can find the, in that 1h means you are actually adding the mass of electron also with it. This is the technique. I think you might have discussed this in the preliminary sections. So you will be getting it as mass of 1h plus mass of n. This 1h means it is sum of proton plus electron minus mass of 2h. This value you know, this no, adding, subtracting this one into c square, you will be getting the energy, and that energy you are getting as 2.224. And we have already mentioned the mass spectrograph. And we can also determine this binding energy directly by bringing a proton and a neutron together to form a deuteron and measuring the energy of the gamma ray photon that is emitted. So when they are forming a compound nucleus, that means deuteron is formed, energy will be released, and that energy is emitted as gamma. The reduced binding energy, which is equal to the observed energy of photon less a small recoil correction, is nearly this value. You can measure that gamma ray energy, and this you are doing at very high energies, normally termed as the Nucleon scattering experiments. It is also in agreement with the mass spectrographic value. A third method called photodissociation, reverse of this process. Actually, here you have a 2H and a gamma is impinging on it, and by absorbing that gamma, this deuteron can dissociate into a proton and a neutron, in which gamma ray photon breaks apart a deuteron. The minimum gamma ray energy that accomplishes this process is equal to the binding energy. Again, we have to correct for the recoil of final products, but it is somewhat low. The observed value is again 2.224, near to this value. Now about the angular momentum. The angular momentum quantum number, or the nuclear spin of the ground state of the deuteron, is 1. It suggests that the spins are parallel. You have a proton and a neutron. If the spins are anti-parallel, it should be 0. But we are getting it as 1, so the spin is parallel. The angular momentum of nuclear ground state can be determined by a number of optical, radio frequency, and microwave methods. Parity. The parity of nuclear state cannot be determined directly. It can be determined indirectly by the studies of nuclear reactions and disintegrations in which the parity changes. It has been determined that deuteron ground state is determined by even parity wave function. That is, parity of deuteron is even. Deuteron quadrupole moment. Deuteron shows a quadrupole moment. That means electric quadrupole moment. This shows a departure from spherical symmetry of charge distribution. Your shape of deuteron is not spherical. The quadrupole moment of deuteron is determined by radio frequency, molecular beam method. And the magnetic dipole moment. The magnetic dipole moment of deuteron can be measured by resonance absorption method. It is found that the sum of magnetic dipole moments of proton and neutron do not exactly equal to magnetic moment of deuteron. Actually, a deuteron is formed by proton and neutron. If you add the magnetic moment of proton to the magnetic moment of neutron, that sum is not equal to the magnetic dipole moment of deuteron. And that's all in this lecture. Thank you.